जैसा सुरेंद्र को बोलते क्विज। हेलो हाँ, so in the next quiz we will have a Friday only. Friday, let me check the date. Friday you have 19th, so you have 19th date Friday 4:30 to 5 o'clock. Okay, so yeah, I didn't right now had given a thought about the questions, so I don't know what about that. That will be surprise only on that day, numbers or whatever is that. So but of course in 30 minutes you can answer the quiz well. Yeah, probably 3 to 4 questions. Okay, so I don't know right now. So yeah, whatever the other engagement is there, please tell them that you have a class scheduled class at 4:30 to 5:30, so that other teachers can arrange that time. Okay, so because already I told you before also, this 4:30 to 5:30 time we want to use it for our purpose only. So you just inform them that at 4:30 to 5:30 we'll have a either class or either we have a quiz or whatever is that. So on the Friday you don't engage your other activity, so you should inform to other teacher as well. Is it clear? Okay. Now yeah, that will be MCQ based only. Okay, objective question only, MCQ based only. Maybe you have to do rough in front of you. So okay, so now let me summarize the Fisher, Newman and Sahor's projection formula. So that no IPC, no. We are much more interested about the stereochemistry. So in the name actually you have a EZ. So basically that stereochemistry is much more important at this point of time. Okay, so IPC you should know it, that is fine, but my concern is very much on the stereochemistry part, whether you are able to answer about the EZ stereochemistry, syn anti, DL, RS or not, or interconversion or not. So basically these four concept, basically EZ, DL, RS and the interconversion is important for you. Yeah, in quiz the questions will come basically based on the EZ only, not the nomenclature based. So don't worry about the nomenclature name. Is it clear? Okay. Okay. So already we discussed, and this slide is already with you, and we have discussed when E and Z we can assign. Okay, so when the EZ we can assign, syn anti is also the same like EZ when we talk about. So that's fine. Okay, no issue. So now we discuss about the tartaric acid also, and then optical activity like polarized light, how polarized light can pass through with the samples afterwards, dextro or levorotatory. This phenomena is purely experimental. Based on the experimental phenomena, we say that this particular compound or particular sample is optically active. If that compound is optically active, then we try to understand that why that compound is optically active. And then we comes that, okay, that compound is optically active because it has a chiral center. Then what is the chiral center? Then once there comes the case of chiral center, then we understand that there is a mirror image relations and that is non-superimposable. So this we initially we understand this is called chirality. So you have a mirror image. These two compounds are mirror image of each other, and you have in between you have a mirror, and this mirror image is non-superimposable, means this cannot superimpose on each other. So these two are two different compounds. And due to this stereochemistry, due to this 3D spatial arrangement difference, these two compounds are chiral in nature, and that is the reason this compound is optically active. So with that, we try to explain that, okay, when the two compounds having a mirror image and these two is non-superimposable, that is basically the chiral compounds. So we understand that chiral compounds, then we understand that why this compound is chiral, because of carbon is tetrahedral in nature. When we come that carbon is tetrahedral in nature, so this due to this tetrahedral arrangement, the difference in the arrangement in 3D terms creates that it is a chiral compound. So now the good and best example I can say, we can discuss about the glyceraldehyde. And if you say these are the few terms that we should remember in the stereochemistry, that what is chirality? So we understand the chirality by historical perspective, like handedness, the mirror image of these two hand, what we have shown there. So due to that non-superimposable mirror image, and then what is stereo center or chiral center? What is stereo center and chiral center? So whenever you have a carbon and four groups, like example, you have a CH4. So this compound is called methane. This compound is methane. So let me get the blue pen. Okay. So this compound is methane. Now, if you go and you change this one, so you have a Br. Then also this compound is not chiral. Again you go, you change Cl, Br, hydrogen, hydrogen. This compound is also not chiral. But when you change this one, any one of the hydrogen, now suppose this one I am going to change and this one is fluorine. This compound is chiral. So what we can see, this particular compound mathematically it's a so symmetry. It has a very symmetrical nature. So when we talk about symmetry, then this compound is so symmetry. Now, when you have a one bromine, then it loses some amount of symmetry. When you have a two bromine and chlorine, then it loses further symmetry. And once you have a three, like a fluorine also, bromine also, chlorine also, so now it doesn't have symmetry. So the, the symmetrical order arrangement is actually lost. And now this tetrahedral carbon, this one is actually chiral carbon. Now this carbon is a chiral carbon. So you see, when we have a simple compound methane, there was a no chirality. Even methyl bromide, no chirality. When chlorobromomethane, no chirality. But when we came here bromochlorofluoromethane, then this compound become chiral, because the tetrahedral nature this compound created in such a way so that the two isomer can exist, and both isomer will have a mirror image relation. Further, both isomers may not superimpose on each other. That is the reason that chirality came. So basically, stereo center and chiral center, these two terminology came here on this card. So we try to understand that how we can explain the chirality, and in a very general way we say that when you have a carbon and all four groups are different, that carbon is chiral. But now we understand that yes, there is some role of symmetry. And when your molecule is so symmetrical, it may not have a chirality. When you have a dissymmetry, then chirality comes. And that chiral center is called asymmetric carbon as well, because it is created limited symmetry. And that limited symmetry, this is special case, that's why we call asymmetric center. So the chiral center, it is called as asymmetric center also, because it has a limited symmetry, may not have symmetry also, only C1 axis. C1 means when you rotate this compound with 360 degree, then only original you can see back. So you have a symmetry axis, but that is a C1. So that C1 means 360 rotation. and that is a limited symmetry that we cannot consider as a symmetry. So I would like to say that when you lose symmetry, then a special case arises, and that special case is nothing but it's a chiral center and it's a stereo center. Because now you have a mirror image relations, like example, you have this carbon and this carbon having a 4 different group, hydroxy, aldehyde, hydrogen, CH2H, all 4 groups are different. This 4 groups difference makes this molecule chiral, first thing. And second thing, that this particular carbon is called chiral center. Second thing, that this molecule having another molecule which having a OH left side. So you see these two molecules is mirror image of each other. Now question is that whether these two molecule is superimposable? No, it's not superimposable. Now second question, if it is not superimposable, then can we consider this two molecule is the same molecule? No, this molecule is not a same molecule. This molecule is entirely different molecule. So these two molecules is not a same molecule, but it creates a confusion. It looks like very same. That is the reason that we understand that these two compounds is actually different compounds, looks like same, but it is entirely different compound. So now how we can name it? Glyceraldehyde, okay, it is a glyceraldehyde. It is a glyceraldehyde. This compound is also glyceraldehyde, but we cannot call glyceraldehyde. Why we cannot call? Because both is a glyceraldehyde, but both is a different compound. So we need to name it. Now, one way we can name it like that. This compound rotates the plane polarized light in the right direction. Means this compound is dextrorotatory. Dextrorotatory. Now, this compound rotates plane polarized light in the left direction. So this compound is levorotatory. So now it is clear based on the optical property. Optical property is purely experimental phenomena. Based on the optical property, we can call it dextroglyceraldehyde. We can call it levoglyceraldehyde. Fine, that is fine. But only thing is that when we say dextro, when we say levo, it means we have to do experimentation only. Because without experimentation, you cannot say dextro or levo. Dextro and levo is the pure experimental phenomena. When your compound will go in the plane polarized light, then your light will rotate right or left. Accordingly, you can say dextro or levo. So what is the limitation? Here, limitation is that just by looking the structure, I can't say this is dextro or levo. So how I can name it? We cannot name based on the dextro levo because this is the experimental phenomena. So just by visualizing, we cannot name it and we cannot distinguish these two. That is the reason that we had given the relative configuration nomenclature and we say that this OH is right side. Then we can call it D. This OH is left side. Then we can call it L. Okay, now this is fine. You see, because dextro and levo is purely experimental, that is the reason that dextro and levo is not a right way to name the compound, two different compound, but D and L is the right way because with the help of D and L, we can identify these two compound. We can identify these two compound. We can say that this is D-glyceraldehyde because the hydroxy is right side. This hydroxy is left side. So this is a L-glyceraldehyde. So means we have now how to name these two compounds. There is a method. There is a method to name it. There is a method to identify these two. But now question is that when we say D means we say that hydroxy right side, hydroxy left side. So all compounds may not have hydroxy. Like example, now suppose here I am drawing one compound. I am drawing suppose Br, fluorine, chlorine, hydrogen, and I am drawing the mirror image. Let me draw. Now Br, chlorine, fluorine, hydrogen. Now you see, this is compound number 1, compound number 2. Now my question is that, can I say D or L? Something like that in this case. Key 1 is D and 2 is L. Can I say like that? Absolutely not. Yes, you all are correct. Absolutely not. Why? Because here hydroxy is not there. CH2OH is not there. So our D and L system is going to fail at this point. So we understand, but we know we have to name this compound. Now, name is that we have bromochlorofluoromethane. This also bromochlorofluoromethane. But both name is same. So we have to name it. But we cannot name it now dextrolivo because that is experimental. We cannot name it like DL because DL requires the special case like hydroxy position. So that is the reason that at this point of time, we have to use the absolute configuration, that is your RS nomenclature. So when we use RS nomenclature means that is a absolute configuration nomenclature that will work out and we can name this compound. Now my next question is that now you have a compound. Let me suppose you have compound. Sorry. So I don't know why my pen is not working. Let me see. Okay. So now let me draw one compound. Is it okay to visualize this compound? What I am drawing, is it okay for you all to see clearly? So now I want that priority. So we have to check the priority that which one is heavy or which one having a more atomic number. So bromine is most heavy and atomic number is high. So let me draw and let me give the number. This is number 1. This is number 2. Priority I am giving CIP rule. And this is priority number 3. So 1, 2, 3. And last priority is 4. Now my next question is that hydrogen is a fourth priority group as per CIP rule, as per the RS nomenclature rule. Your fourth priority group should be away from you. Now my next question is that whether your fourth priority group hydrogen is away or not, or front. So I'm asking a question that whether this hydrogen is away or front. It's a behind or front. ये हाइड्रोजन कहाँ पे है? Whether it is in front or back side. Okay. So in the Fisher projection formula, what we need to remember, horizontal line is always front. Horizontal line is always front. So whenever we draw Fisher projection formula, this particular two groups which is on horizontal line, that is front, and those which is vertical line which is behind. So we need to remember this thing. So your vertical line is behind and your horizontal line is front. If your horizontal line means front, as per CIP rule, as per RS nomenclature rule, your fourth priority group should be behind. So one thing is contradictory right here, that as per the CIP rule, as per the RS nomenclature, your fourth priority should be away, but it is not the case at this point. So now we all know that priority group is 1, 2, 3. So this is clockwise or anti-clockwise? This is clockwise or anti-clockwise? Anti-clock. So if it is anti-clock, as per the anti-clock, it should be S. It should be S configuration. So we are talking about a RS configuration. So it should be S configuration. But as per the rule, anti-clock should be S, but fourth priority group should be behind. But it is not the case. Fourth priority group is front. So that is the reason S is wrong. Why? Because your fourth priority group is not behind, is front. So that is the reason anti-clock means S, but your fourth priority group is on horizontal line. That is the reason this configuration is R. So this particular chiral center, the configuration is R configuration. So okay, so let me very simple. Whenever you have any compound like CH, BrClF, this is your compound. I can say C, I can draw something like this. You have a H, you have a Cl, you have a Br, you have a F. Now, I would like to say that draw in Fisher projection formula. Fisher projection formula. What is Fisher projection formula? Fisher projection formula means your carbon you need to draw in this manner only, plus manner. So whenever you draw, so you draw very simple, you have to draw your Fisher projection formula something like this. So what I am going to draw, anything I can draw, wherever I want I can write something and I can draw like this. So this is the compound what I draw. I want, I can draw very simple like whatever we draw before. Yeah, this one I can draw like this. This is also. So now your compound number 1 you have, compound number 2 you have. Now question is that 1 and 2 are same or different? First thing. Okay, to decide that 1 and 2 is same or different, what we need to do, because we understand that this carbon having a 4 group and this 4 group is different, so this particular carbon is a chiral center. So now we have identified the carbon, that this carbon is chiral center. So now once you identified that carbon is a chiral center, means to understand these two compound is same or different, you need to find out the right configuration. So what we need to find, whether these two compound is R or S in terms of configuration. So now next question is that how to find out the configuration. So what we can do now, Fisher projection formula, it has a rule. Fisher projection formula means your carbon having a 2 group, one is a horizontal line, and one is a vertical line. So vertical line means behind and horizontal line means front. These things we must remember for Fisher projection formula. Okay, we are drawing very simple way like this. Hydrogen, chlorine, bromine, chlorine. But we need to understand that bromine and chlorine is front. Hydrogen and fluorine is behind. These things we must remember in the Fisher projection formula. But why? Because actually this is the Fisher projection formula. And this Fisher projection formula means this bond is called beta bond. This bond is called beta bond and this bond is called alpha bond. Beta bond means above the plane, alpha bond means below the plane. So your monitor, your screen is basically plane. But your bromine and chlorine is not on the same plane. What does it mean? It means what I am right now able to visualize on the screen, that I have a bromine and chlorine and fluorine and hydrogen. All four are not on the same plane, not on my screen. Bromine and chlorine are front, means above the screen, and hydrogen and fluorine is the behind the screen. Actually, this is the 3D understanding we should utilize when we try to understand any Fisher projection formula. So this is the first concept we should understand in the Fisher, that horizontal line is front and vertical line is behind. Now go for second step. So first you have identified which is front, which is behind, or as per CIP rule, first we have to give the priority. First we have to give the priority. After priority, you have to check that whether clockwise or anti-clockwise. If clockwise, then it is actually R. If anti-clockwise, it is S. But what is the condition? Condition is that fourth priority group should be away. Fourth priority group should be away, behind. If this clause, if this condition will be work out, then only your clockwise will be R, anti-clockwise will be S. If not, then your clockwise will be S, anti-clockwise will be R. So whenever you check your priority 1, 2, 3, then you have to find out whether clockwise or anti-clockwise. If it is a clockwise, then you have to check whether your fourth priority group is front or behind. If it is a front, then you cannot make R for clockwise. You can make the R only when your fourth priority group is away. So am I clear about this? Good. Okay. So nice. So now I would like to give the, because I don't know this 1 and 2 is same or different. So what I need to do, I need to give first priority. So what I am going to do, I am going to give first priority to all these compounds. So bromine atomic number is the maximum. So you have a priority number 1. Chlorine will come in the second number. Fluorine will come in the third number. Hydrogen will come in the fourth number. Now, so now this is clockwise or anti-clockwise. So now this is clockwise. 1, 2, 3. Sorry, 1, 2, 3. This is clockwise. This is clockwise, and fourth priority group is away. So your fourth priority group is behind, so it perfectly matches with the CIP rule, and this carbon will be R because it's a clockwise and your fourth priority group is behind. So it's a R. So now we understand 1 is R. 1 is R. Now let's talk about 2. You have a bromine priority number 1, chlorine priority number 2, fluorine priority number 3. Now tell me 1, 2, 3, this is clock or anti-clock? It's a anti-clockwise. So it should be S, but it is not S. Why? Because fourth priority group is front. So it's anti-clock. It's anti-clock, but it's R. It's anti-clock, but it's R because your fourth priority group is front. It should be away for S. So now 2 is become R. So 1 and 2 is same or different? So 1 and 2 is same. So any two compounds which having a chirality, which having a stereo center, that will be same or different. That depends on the how we are good to determine the RS configuration. if we can determine the RS configuration, then only we can tell 1 and 2 is same or different. In this case, 1 and 2 is same. So this is all about RS configurations. I hope you understand. Now you can make few problems also for RS configuration. So you are now clear for DLRS. Okay. So now you understand that what is the projection formula. So as I explained today, that how we can determine, how we can draw a Fisher projection formula. So what is Fisher projection formula? Fisher projection formula is very simple. We draw in a very simple way, horizontal line and vertical line. Horizontal line means front, vertical line means behind, and using this concept, we can draw the Fisher projection formula. Fisher projection formula is a 2D formula. Why 2D? Because we are drawing in a very simple way, two lines plus. But Sahar's projection formula and Newman formula, flying wedge, zigzag, these all are the 3D formula. Using the 2D plane, we are trying to have a 3D drawing. So that is the reason that whenever we convert Fisher to Sahar's or Sahar's to Fisher, we need to use some rule. Why rule plays here? Why rule comes here? Rule comes because we are trying to draw 3D molecule in 2D plane. That is the reason we need to follow a rule. Because you see, 3D structure is not possible to draw on a plane, 2D plane. That is the reason that we follow some rule so that it may not go wrong. So that is the reason we learn that how to convert Fisher to Sahar's, Sahar's to Newman, back to Fisher like that, and how we can determine the RS configuration. So I hope now if I tell you that simple tartaric acid like this, now my next question is the how many chiral center? How many chiral center? So this is C1 and this is C2, suppose. Two chiral center. Can you tell me C1 will be R or S? Can you tell me C1 will be R or S? So it is better that we can draw exclusively C1. So in the C1 is connected with OH. So oxygen is connected here at this point. Here carbon is connected and here also carbon is there. So if you talk about only C1, then you have a three group. One is a oxygen, one is a carbon, another is a carbon. So oxygen priority will go 1. This carbon priority what will be 2 or 3? This carbon will have a priority 2 or 3. So your this carbon will have a priority 2. Now what about this group? Now you have a total 3 group. You have a now total 3 group. One group is COOH. One group is OH and one is a big group. Now you have a priority 1, 2 and 3. So for C1 if I say, for C1 so if I say C1, then here you have a priority number 1. Down you have a priority number 2. Up you have a priority number 3. Left side we have a priority number 4. So it is clockwise or anti-clockwise. So this clearly looks like clockwise. Clockwise means it is R, but your fourth priority group is front. So this is S. So your C1 is S. So your C1 is S. So how we determine the RS configuration for this particular carbon? What we did, we know that carbon having a total 4 group. All the 4 group we have to give the priority. How we will give the priority? We will see the connectivity. This carbon is connected with oxygen, oxygen having a higher atomic number. Then this carbon is connected with this carbon and here also connected with carbon. So both is a carbon. So on the case of carbon, both is same. So we have to check the other atom. Now this carbon is connected with a oxygen and this carbon is connected with a carbon, but this carbon is connected with a double bond oxygen. So whenever any carbon is connected with a double bond of oxygen, actually as per the rule, it consider carbon is connected with 2 oxygen. It is not connected with 2 oxygen, but only as per the rule, the double bond we give the priority based that this carbon is connected with 2 oxygen. That is the reason that this particular carbon get the higher priority than this group. Why? Because this particular carbon is connected with 1 oxygen, this carbon is connected with 1 carbon, but this carbon is connected with oxygen using double bond. And then this carbon is connected with another oxygen. So actually this carbon is connected with 3 oxygen. It is not connected with 3 oxygen. Only we need to assume as per the rule, CIP rule. So that is the reason that this group got the second priority. And this group get it third priority. So I hope you understand that for each individual chiral center, for each carbon, we need to work carefully to determine RS configuration. For each group, you have to give a priority. For each group, you have to use the CIP rule that which group will have a higher priority. Then you have to check clockwise or anti-clockwise. Then you have to check your fourth priority group is away or behind. And then accordingly, you have to give the R and S configurations. So I hope you all are able to understand this RS configuration so that in any molecule, you can determine the RS configuration. So you can do the practice for just 2 or 3 compounds like tartaric acid is sufficient. How many isomer? You have a 4 isomer of tartaric acid. What you can do practice at your home? You can do the practice using the tartaric acid to determine the RS configuration using our this discussion. No need to remember anything. Just draw on the paper, just get it the RS configuration. Just follow the pathways what we discuss. So am I clear to you all? You getting the things that how you can determine the RS configuration? If any doubt, please tell me. Or is it clear to you all? Good. Okay. So now let me just finalize only. Okay. Okay, Nishank. So, okay, I will tell you later in the next class that how we can transfer the wedge bonds to the fissure. Okay, because it will take little bit time to explain it. So in next class I will do, but I will clarify that your double bond case that Suppose you have CHO and here you have a CH2OH. Okay, now is tell me that in these which one will have a higher priority? This is carbon, this is also carbon. So which one will have a higher priority? CHO will have a higher priority. Why? Because now I can draw like this. You see C double bond O bond H. And this one I can draw CH2OH. So if you see carefully about this chiral center is connected with this carbon. This carbon is connected with one oxygen. But here if you go with this carbon, this is connected with double bond oxygen. Actually, double bond oxygen means there is a two oxygen just for assumption, arbitrary. In reality, it is not there. But this carbon is connected with double bond oxygen. It means this carbon is connected with two oxygen. That is the reason this CHO gets the priority 1 and CH2OH gets the priority 2. Whenever you have a double bond, whenever you have a triple bond, as many numbers you need to consider that atom. Okay. Okay, so now means as I said that you have to transfer it. Like example, suppose you have a compound. Can you transform this one to Sohor's projection formula? What we need to do? This one will consider one number. This one will consider two number. And just we will draw like this. One number is this one and two number is this one. And CHO is down, so we'll make it down, CHO. Hydrogen and bromine is left hydrogen and bromine is right side. Now, in the two number carbon, this one, what we need to do? Down eclipse we need to make, and what we need to do? CHO is up, but we need to make it down. These things only we have to follow. Whenever you are transferring from the Fisher to Newman, because this is a 2D, this is a 3D. So you have to follow this way, and rest thing is same. So your bromine is left side and your hydrogen is right side. That's it. This is your Sohor's projection formula. Now, this is like a watch dial. This is like a watch dial. This dial you can rotate as much you want. So if I say draw in staggered form, you can draw easily. What you can do? CHO is here, hydrogen is here, Br is here. You can rotate this CHO. You can rotate this CHO vertically up. And if you rotate this CHO, then these two will go down and left side will come H and right side will come Br. That's it. Staggered form is ready. So, but only thing is that don't go Fisher directly to staggered. It you can do mistake. You can do wrong. So what you need to do? First you prepare a eclipse structure. Then whatever the question says, you can do because rotation is free. Proper rotation means CHO is rotating 60°. Bromine will also rotate 60°. Hydrogen will also rotate 60°. So accordingly, like a watch dial, you can rotate either front one or the back one, and you can draw whatever the structure you want. So based on that, you have to do the conversion. Whatever Fisher Sohor's or back Sohor's to Fisher. Now, question is that if I had given you structure number 1 and I am saying that draw the Fisher. So what you have to do? First, you have to convert 1 to 2 eclipse. This one. And then from this eclipse, directly you can convert to Fisher. The same way what we did. Then only you will make the correct answer. So whenever you are doing this transfer, be careful about it. And because this is a 3D projection formula, so directly you can transfer this one to Newman projection. So if I ask not Sahars, if I ask Newman, then it's very easy that this one easily can draw in Newman projection formula. Very simple, that the front one you have already. So in the front one you have already this one. So your CHO is down, your left side hydrogen, right side bromine, and in this CHO is here. CHO is here, and then hydrogen is left side, and bromine is right side. So you see, when we draw, suppose I have asked a question that you need to draw a staggered form of this structure in Newman projection. So when you draw Sahars, then directly it can go to Newman directly. No need down eclipse or anything. Why? Because this is also 3D. This is also 3D. There is no rule. Directly it can transfer to Newman. But when you want to come back, Newman to Fisher back, then again you have to draw Newman eclipse down. And once you prepare eclipse, then you should go for Fisher, so that there is no chance to have a wrong structure. Okay, so I hope you all are able to understand this RS configurations, DL configurations, interconversion, or any doubt. Okay, so okay then, now we can conclude our sessions, and we'll be ready for only from Weiss dash to Fisher, that we will discuss in the after quiz class. Okay, so that flying Weiss to Fisher we can discuss in the next time. Okay, is it okay? Yes, I will upload that PPT. Okay, thank you then.